So our next speaker is me. But I'm speaking on behalf of my colleague, Jeff Quast. So I'm going to give him an introduction, which is less awkward than introducing myself. So Jeff is a colleague based in Midland, in Michigan, in the US. He's supporting our customers in North. He's especially specializing in, I would say, the alternative applications, not the typical structural glazing, insulating glass, and weatherproofing sealants, but like the hybrid technologies, the polyurethane we are going to see today. And as a background, I think he's a material scientist. He has a PhD in this. He's done, since 2010, when he joined Dow, a lot of different roles, worked in semiconductors as well, so this suits him very well. So today he will talk to me about stress distribution in glass railing systems, which are wet glazed. So what are we talking about? It's this kind of applications. So the high-end residential hotels, balcony types, where you don't want anything obstructing the nice view. So you want a full glass balustrade. No metal fixation. Can be obviously also in other applications. It's quite popular today. And I must say, I have a very old balcony with a glass fixed with metal. I wouldn't mind to give my balcony as a test. So what is the application itself? So normally we can use grout to do the embedding. We are offering here to use a two-part self-leveling polyurethane, so it's called 375. The nice thing about it is, as it is really very liquid, you can apply it from one side. It will really nicely go on the other side once you've installed the glass. It's a polyurethane, so it doesn't come with the normal durability of a silicone, so we are topping it off with a 791 weatherproofing sealant or a fire-rated solution, depending on what you're looking for. It comes in a toffee color, but you can also pigment it black if you prefer this. And normally we recommend to have a release agent on the glass to facilitate removing the glass if it would be broken. Now, obviously, you're familiar with the type of test that this application requires. You need to be safe, so you need to resist mainly the line load that is brought by people leaning on a balcony. Resist soft body impact test. There are kind of a lot of different tests that you need to do. And obviously different system parameters, which all have an influence. So if every time you need to do a full-scale mock-up, it's not always easy, and the extrapolation of results to different values for your parameters can limit the use of these tests. Also, when we are dealing with a polymer for the embedding, we want to understand really how this whole functionality is going to affect our material, potentially, how we have stress distribution in the polymer. So here you see that, okay, we've only tested it once, it's a repeat. It's not like systematic, but this type of test we really need now to validate finite dimension analysis models, which is one of our favorite activities. We do a few experimental tests. We build a model. We validate that we predict with the model the same results as with your experiment. And once you're good to go, you can vary all your parameters without having to do all these tests. The ultimate goal is to facilitate our life of Dow people that have to dimension so that we create semi-empirical Excel type of analytical equations that avoid us to use FEA, that gives immediately feedback to very urgent requests from customers about what dimensions we need to give for polyurethane. Now, it's a polyurethane, so it's a bit different than what we are used to. So when we wanted to do the material model that we need for the FEA, we had a bit different testing to go through. Obviously, the uniaxial test pieces, but to also concentrate a lot on compression. looked at those values, how it changed, the yielding strength, so really when it starts to permanently deform, the Poisson ratio, it's not like nearly incompressible like a silicone, and also the CTE, so the way it changes with temperature. So there's a lot of testing going behind the development of our material data. So this is what we use for this material in terms of modulus. The elastic tension and compression modulus are more or less similar. And this is the type of stress strain curve that we will have. And we are using for the modeling in the 3 areas, 3 different equations with the parameters that are provided here on the left. The yielding stress, there are different definitions to say when you really will have a permanent damage. You could use this value, which is based on the ASTM standard, or you could use this one. So obviously, one is very conservative, the other one may be a bit too free. So we have an average here that we are using for our material. So in the next step, we have taken the test report that was done previously on the material, and we have used this to build a model and get, hopefully, to the same results under the line load and on the hard body impact. These experiments were not intended at the beginning as a validation of an FEA. We were not present. It was done in Italy. The modeling was done in the US. So makes it a bit more difficult to really understand all the details of the installation. And we saw that this really could have a big impact on the results. So here you see the typical setup, the type of glass that we have, the dimensions for the 375 and 791, where we measure the deflection and the observations. So what did we see? When we applied the 3 kilonewton line load, which is the maximum you need to resist at the level of the actuators, is that our model predicted, for example, only 30 mm of deflection, and we knew that experimentally we had measured 50 mm. So that was really a first observation. We made the assumption that the bottom surface of the rail had been completely fixed. We changed that, made 4 corners of the rail fixation so that the deflection would increase. So there's really a bit of work if you have not optimized from the start your experiment and you don't know exactly. So you have to play around until that model really works. So we got to that eventually. Also validated that when you have a 1 kg hard body impact, that you see how the stress distributes in the glass, that you don't have the glass breakage, and that we, especially at the level of the polyurethane, are not going to exceed our maximum value that we want to accept. So quite some work to validate this model, also a bit different type of application than what we do normally, but it was okay. And in the next step, we did a DOE. So we took the different parameters, and our goal is always to cover 80% of the projects, not everything, otherwise you run in way too many variations that you need to simulate. So we always go as well for a worst case approach. For our material, we make assumptions that will increase the stress potentially at the level of the polyurethane, because that's the ultimate goal. We want to be sure that it's not going to be damaged during its lifetime. So we assume, for example, that everyone is fully bonded. So the polyurethane, the glass, the aluminium, although we recommend to have this release agent, so it's a worst case scenario. And we changed here the line load, the wind load. We varied it between 1 and 6 kPa. And we have the line load as well that was between 1 and 3 kilonewton. We did not combine them in this DOE, all these loads, so it was or the line load or the wind load. The rationale is a bit, we'll see it later, we checked, but if you're outside 3 kilonewton, you typically will not have a 6 kPa wind load, so we don't combine them. And here you see 3 meter. This is more to simulate a windscreen and not really a balustrade. So obviously, we run all the combinations, so sometimes you have a bit weird combinations. Again, I'm using that word a lot. So how does it look, the type of output that you get? You have the polyurethane stress, which is the information we want to verify that remains below a certain yielding point as a function of the different parameters that we have varied. And you can see, for example, that the polyurethane thickness is varied between 10 and 20 mm, but there's like a flat line, so it doesn't have really the biggest impact. We see that the glass thickness, as expected, if it's very thick, it's not going to move that much. So it's going to lead to reduced polyurethane stress. But then the others, they can have a less linear relationship. So it's important to realize that we do not want, certainly not these parameters, to look outside of the DOE range. If I say that, I'm going to be killed by some experts. You never go outside of a DOE range because potentially your equation is doing weird stuff. It's only maths and not physical. But still, we could say that, okay, if you have a thickness that is a bit higher, it doesn't matter, you know it, you will be on the safe side. On the other hand, if we have 7 kPa, we are not going to use this equation for dimensioning. So we have a predicted function, an equation that gives us easily how much the stress is when we get the parameters for a certain project. Similarly, we can output whatever we want with FEA, so we looked at the deflection of the glass. We do not have the ambition to make a recommendation on the glass, it's not our job, but since the information is there, we are just doing a quick check versus national regulations, just to be sure that you're safe enough, far away from what is tolerated in this type of application. If it's not the case, we will mention it, that it might be a good idea to double check these values with a glass engineer. So similarly, we have the glass deflection as a function of the different parameters that is available to our TSND. Now, as I said, this is for covering 80% of projects. Most of the time you have exceptions, like 100% of the time. So we want to see really what happens if you get to worst case scenario. So we played a bit with single cases. We took a very low PU thickness, only 6 mm. We took 75 mm, so lower embedded depth. And we play with the combination of the loads. So, for example, here you see that the PU stress, if you have only the wind load, you're very low in comparison to the threshold that we authorize. If you're at 6 kPa, this design would already be not accepted by DOE. But we wanted to see what happens if, in a worst case, you add the line load. Must be sure I don't fall here. So you see here, adding the line load to the low wind load, it's not making a bit difference. You're still safe. But this is really interesting to see that it doesn't matter that much. Glass deflection, again, just for information, we are not going to use this or make an official recommendation or approval on basis of this. We also played around with the height of the wind load, so it's also interesting to see how much tolerance you have. The standard for the balustrades gives you a certain height, but obviously if it's different, how is it going to affect my polyurethane stress? And should we, in that case, if a customer says, I want it to be for 1.6 meter, should we be aware of something? Should we highlight it? Do we need to do a specific FEA? That was a bit the reason why we did these individual cases, is to understand in what case there's a potential risk and we want then to look at it in more detail. We also looked at, for example, when the polyurethane has not been well mixed, we know that this is going to impact the modulus. We have customers where it occurred. It could also occur if you leave the polyurethane without any protection and there's water, it will also soften. So how is it going to affect all these results? What happens if you have an embedded depth that is too low versus our general recommendation, or the thickness, and the clamping of the rail as well. So we have all this information to help our internal design team. So a typical example is, for example, here the Hotel Dios in Mykonos in Greece. So they used it for this windscreen. It facilitated, obviously, the whole approval process to have access to these equations, to check that the glass deflection was accepted and can, in certain cases, also avoid you to do any testing. So these are the most typical applications, balustrades, windshields, but I think it's interesting to open and conclude the talk here with another use of this material. So here it's been used to embed the glasses here that encase this big sculpture, glass sculpture. It's in a museum dedicated to Brancusi sculpture in Craiova. And it's been standing since 2019. And we believe it's one of the largest embedded cases. So it's showing you that the material has quite some possibilities. Thank you for your attention.